Hello there, welcome to A-Level Further Maths. Here we're looking at the start of the Maclaurin series chapter, so we can answer questions from exercise 2C. So who was Maclaurin? So this was Colin Maclaurin. He was a Scottish professor between 1698, well, he was born in 1698 and 1746. He was a child prodigy and entered university aged 11 and was elected professor of mathematics at age 19 in a 10-day maths competition at Aberdeen University. This was the youngest professor to have lived up until March 2008, so he held that record for a very long time. And he was recommended to Edinburgh University by Isaac Newton, who was so impressed he offered to pay his salary himself. So he was a contemporary of Isaac Newton, and he was around at the forefront of when differentiation and integration started to really pick up. So Maclaurin series is to do with differentiating. And what Maclaurin thought was, could I use this newly discovered differentiation to write sine x as a summation of powers of x, or a polynomial? So something plus something x plus something x squared, something like this. Could I write sine like this, where it's just an infinite series of powers of x and then something multiplying by those powers at the start? So what we're looking at here is a big long summation of polynomials. That's why this chapter is in the series chapter. So it's called Maclaurin series because it was Colin Maclaurin that invented it, and it's a series or an addition, maybe a subtraction. These numbers that are in front of x or x squared or x cubed could be negative, so it could be a subtraction of powers of x. Okay, so what we'll do then is we'll start by assuming that sine can be written like this. Sine x equals something plus something x plus something x squared plus something x cubed plus something x to the 4 plus something x to the 5. And as I've said, any of these somethings could be negative numbers. So I'm saying add, but it could also be a subtract. Now, generally what we want to do in mathematics is when we don't know the value of something, we put a letter in there. We use algebra to represent those things that we don't know. So the way that we do this typically is we use a0 to represent the coefficient with x to the power of 0, a1 to represent the coefficient of x to the 1, a2 to represent the coefficient of x squared, a3 to represent the coefficient of x3, a4 to represent the coefficient of x to the 4, etc, etc. Okay, let's now start to think of what these letters could be equal to. So what I'll do first is I'm going to substitute in x equals 0, and I'll see what happens. I'll substitute it in on the left hand side, so sine 0 equals a0 plus a1 times 0 plus a2 times 0 squared plus a3 times 0 cubed plus a4 times a0 to the 4. And what you'll see there is just a lot of zeros. We'll just cancel out most of this. So actually, therefore, sine of 0 will just equal a0, so a0 is 0. So the first number in the Maclaurin series for sine is 0. And don't worry, it's not all going to be 0, that would be just silly. The first bit will be 0. Let's now move on to what a1 might be, and how could we work out what a1 is? Well, as I said before, Maclaurin was at the forefront of differentiation. So what we're going to do with sine is differentiate it. So we're going to differentiate everything. Sine x differentiates to cos x. A0 is just a number, so it just differentiates to nothing. A1x will differentiate to a1. A2x squared, well, x squared differentiates to 2x, so it would be 2 times a2x. X cubed differentiates to 3x squared, so that would be 3a3x squared. X to the 4 differentiates to 4x cubed, so that would be 4a4x cubed, and etc, etc. And then again, we'll put in 0. We're always going to be putting in 0. So substitute in 0. 0 is a really helpful number to put in because any power of x will just cancel out. So it's always going to be substituting in 0. So here we can see that cos of 0 will equal a1 because the rest of it will just simplify out. So a1, the next term in the sequence, will be the number 1. So I've worked out the first two coefficients in my sequence, and just through this pattern of differentiating and then subbing in 0, I can work out the next numbers in the Maclaurin series expansion. So again, we differentiate, and we get minus sine x. Cos x differentiates to minus sine x. So when we differentiate, we get this summation here. The a1 disappears because it's just a number. 2ax differentiates to just 2a2. 3a3x squared. Well, the x squared would differentiate to 2x, so it would be 3 times 2, a3x. And you can see here, once we've differentiated it twice, we've got two numbers that are multiplying because it's the coefficient is multiplied once by the power and then a second time by the power, the reduced power, once we've differentiated it twice. And that will happen for all the numbers in this chain of powers of x. And again, we substitute in 0, so it's minus sine 0 will equal this thing at the front here. Everything else will just be simplified out because we're subbing in 0. That's the whole idea of subbing in 0. So therefore, minus 0 on the left-hand side will equal 2a2, so therefore a2 must be 0. So the next term in the sequence will be 0. So we've got the first 3 now. Let's just carry on and do a few more, and then you might be able to see the pattern here. Differentiate again. So minus sine will differentiate to minus cos. And you'll see here we've now got 3 terms that are being multiplied at the front here because we've had to differentiate 3 times. So it's going to be 3 times 2 times 1, a3, plus 4 times 3 times 2, a4x. You can see here that the 2 would multiply to the front and then reduce the power by 1, and the 3 would multiply here and then reduce the power by 1. And then again, sub in 0. So we're going to get minus 1 equals this coefficient at the front here. So 3 times 2 times 1. That's familiar because the exclamation notation, 3 factorial, actually represents 3 times 2 times 1. It means start at that number 3 and then multiply every single number downwards from that number 3. So this expression here could be simplified to 3 factorial. So it's going to be minus 1, because it was minus cos of 0, over 3 factorial. So that's the next number in this sequence. So it's a fraction, it's not a big number, it's a small number. Let's move on to the next one. We've got 2 more to go here. So Maclaurin kept on going. He differentiated again. Minus cos will equal sine x. It goes back round in a circle. And then the power on the 1 here will multiply into the bracket. And the power of 2 here will multiply into this bracket. So every term in this sequence now has 4 numbers multiplied together. Sub in 0 again. And then we'll get 0 equals, when you put in 0, everything else after the first term will disappear. And we get 4 times 3 times 2 times 1, a4. So it's 0 divided by 4 factorial. Well, that's just 0, isn't it? So it's again just 0. We'll do one final one, so I'll bunch them all up and we'll now again differentiate. We could go on if we want to, but this will be the final one. Sub in 0. You'll be able to tell that everything past the dot 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 will just be 0 because we'll be subbing in 0. And you can see here that after the next differentiation, the 1 here will simplify, will multiply the coefficients and then reduce the power by 1. So it's 5 times 4 times 3 times 2 times 1 after 5 lots of differentiation. So this expression here can be simplified to 5 factorial. So what you can see here is that the number of times you differentiate, you're going to be dividing by that number of differentiations factorial. So here, because cos of 0 is equal to 1, then we divide this thing onto the other side, we're going to get 1 divided by 5 factorial. So the sine expansion up to the power of 5 is equal to 0 plus 1x plus 0x squared minus 1 over 3 factorial x cubed plus 0x to the 4 plus 1 over 5 factorial x to the 5. And you can carry that sequence on and on and on. And Maclaurin's did it just to make double sure that he knew the pattern. And this is the pattern here. You can see the pattern is x minus 1 over 3 3 factorial x cubed. I've cancelled out all the zeros here. Plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7 plus 1 over 9 factorial x to the 9 minus 1 over 11 factorial x to the 11. And then it goes in that pattern of plus minus plus minus plus minus across all of the odd factorial reciprocals and odd powers of x as well. And in fact, you can do this to any function as long as you can differentiate the function and then substitute in 0. You could do this for any function. You can do it for cos as well. And cos nicely complements the sine one, actually. It starts at 1, then it's minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4, minus 1 over 6 factorial x to the 6, plus 1 over 8 factorial x to the 8, minus 1 over 10 factorial x to the 10, and then it goes in that pattern of plus minus plus minus plus minus across all the even numbers, reciprocal factorials, and powers of x as well. So let's just show you that it can work for any function. And what would it be if I was to do the Maclaurin series expansion for any function? So Maclaurin wasn't just happy at stopping at sine and cos, he wanted it to prove it for all functions. That's what mathematicians do. They want to prove things for the general family of functions or family of mathematics that they're working in. They don't want to just prove it for individual cases. So Maclaurin started with any function f of x can be represented as the summation of powers of x. And again, he did a similar process of using letters to represent those unknown coefficients on the powers of x. And he went through exactly the same process as he did for sine. He substituted in 0, then differentiated. Substituted in 0, then differentiated. Substitute in 0 is differentiated, etc., etc. So when we substitute in 0 this time, we're going to get whatever the function evaluated at 0 is will be equivalent to a0. So at the moment we've got our function is equal to f of 0 plus the rest of the series. Let's work out what the rest of the series is now equal to. We do this by differentiating. So we differentiate once. Similar to the last time, we substitute in 0. So it's going to be f dash of 0s. Remember the notation for differentiating in function notation is just a dash, so that little dash there just means I've differentiated my function once. So it's f dash of 0 is equal to a1 plus everything else that's being multiplied by 0, so then a1 must equal f dash of 0. This means differentiate the function once and then substitute 0 in as x. So we've got here, we're building up the sequence now. We've got our function of f of x is equal to f of 0 plus f dash of 0 x. These will be evaluated to numbers. Whatever the function is evaluated at 0 will be the first term. Then whatever the differentiated function will be evaluated at 0 will be the number that goes in front of x. Let's work out what the rest of the numbers are. We differentiate again and then substitute in 0. So we differentiate again, and on each term is going to be multiplied by one new factor. So you can see here it's going to be 2 times 1, but I just didn't write the 2 times 1. It's 3 times 2 and 4 times 3 and 5 times 4. The next one will be 6 times 5, etc., etc. And the powers are knocking down by 1 each time. So they've knocked down by 2 in total because we differentiated twice. We substitute in 0 again and we get f double dash of 0 equals 2a2. The rest will be multiplied by 0. So a2, we're now going to have to start dividing by these coefficients that are at the front through the differentiation. So it's going to be f dash dash of 0 over 2. So that means differentiate the function twice and then substitute in x equals 0. Then divide that number by 2. So at the moment, this is the term we've just worked out. Let's now go and work out a3. a3 can be worked out by differentiating again and substituting in 0. So we'll differentiate again. Every single term will have a new number multiplied into the coefficients through the differentiating process. Substitute in 0 and we get the f triple dash of 0 will equal 3 times 2 times 1, a3 plus everything else will have a 0 times in it. So we can remember simplify 3 times 2 times 1 to 3 factorial, and then a3 will therefore be equivalent to f triple dash 0 over 3 factorial. So you can see here there's a nice little pattern. The third coefficient, starting at 0 coefficients, so the third coefficient will be equal to 3 differentials, put 0 in, divided by 3 factorial. And as long as you can spot that pattern, we'll see it once or twice more, then you can see that there's a pattern in the Maclaurin series expansion. If you differentiate it again, and then substitute in 0, you can see that exactly the same pattern will happen again. The fourth coefficient in the sequence will be equal to 4 differentials of f, put in the number 0, then divide it by 4 factorial. It's all the 4's here. 4, 4, 4, a4 equals 4 differentials, put in 0, divided by 4 factorial. So you can kind of see the pattern that's now being established here. We'll do one more, differentiate once more. We've got 5 factorial times a5 here when you differentiate 5 times. We won't put 5 dashes anymore, we'll just put in brackets 5, and then it would be the fifth coefficient is equal to the fifth differential of f, put in 0, divided by 5 factorial. And there we are. This here is the Maclaurin series expansion for any function that can be differentiated and then have 0 substituted into it. So this is the Maclaurin series formula for all functions that are differentiable, and we can put in x equals 0 into it. So luckily you get this in the formula booklet, so what you need to be able to do is to differentiate functions lots of times, put in 0, and then put in the coefficients here, 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 and here. It's always going to have an increasing power of x on it. You just need to work out what the coefficients are of these x powers. So we've seen the process here, didn't we? We saw that we plugged in 0 first, then we differentiated, then we just repeated this process over and over again, and then you just write out the formula where those coefficients are in front of the power of x. And yeah, luckily you get it in the formula booklet without all the red squiggle over it. You do get it in the formula booklet. So a quick graphical comparison of the summation against the exact values of e to the x. So e to the x can have the same process done to it as well, and it will be 1 plus x squared over 2 factorial plus x 3 over 3 factorial. The more terms you use from the Maclaurin series expansion, the more accurate the graph gets as you draw that graph out. So you can see here, by the time it's got to the final graph, actually e to the x, when it's written out to the power of 5, looks pretty similar to e to the power of x. And if you use more powers of x, then the graph looks more and more similar to the e to the x graph. And the same would happen for sine, cosine, etc., etc. Okay, here's a question for us to have a go at using the maths that we've just looked at. Express ln 1 plus x as an infinite series in ascending powers of x up to and including the x cubed term. So why are we doing ln 1 plus x? Well, if you think about it, ln x differentiates to 1 over x, and you can't put 0 in to 1 over x, because you'd get 1 over 0, which would be impossible to work out. So we don't ever do this Maclaurin series expansion for ln x, we always do it for ln 1 plus x. So what we need to be able to do first is differentiate f of x. F of x here is ln 1 plus x, so if we differentiate it once, then we get the 1 over 1 plus x. You need to be really good at differentiation for this chapter if I haven't mentioned it already. And then we differentiate it again, write it as an indice form, and then differentiate the inside of the function, then multiply it by the differential of the outside. It's the chain rule here. Differentiate inside, then differentiate outside. So we get this expression here. Differentiate it again, and we get, write it in indice form, differentiate the inside, then differentiate the outside. We get that expression there, and we've gone up to the third differential. We only need to go up to the third differential because we're only going up to the x cubed term, because that's what it says to do in the question. Now what we need to do with all of these four terms is put in 0. So we've done the differentiating of all of them, now we'll put in 0 into all of them. So ln of 1 plus 0 is 0. The next one will be 1. The second differential, put in 1 and you'll get minus 1. Put in the third differential, put 1 in and you'll get 2. So now that we have evaluated all of the differentials put in 0, the final bit will now be coming to write out the Maclaurin series formula expansion using these numbers that we've just worked out. So f of x is going to equal f of 0 plus f dash of 0 that's the Maclaurin series expansion, and we'll now use those values. So we're going to write out f of x equals the first term, which is f of 0, which is 0. That would be 0 then. The next term will be f dash of 0, which is 1, so we'll put 1 in front of x. The next one will be f double dash of 0, which will be minus 1, and then we'll put that over 2 factorial, because that's what it says to do in the formula. And then, yeah, we'll carry on that process. So put in 1, put in the second differential, put in the third differential, which was 2, it'll be 2 over 3 factorial. And remember, all of these divide by factorials come from the fact that we've had to differentiate the function 3 times and then divide the coefficient by that number. Okay, whoops, and let's just see that answer. The answer here is x minus 1 over 2x cubed, so x squared, plus 1 over 3 x cubed. So the 2 here will cancel out one of the 2's on the bottom when you write it out as 1 times 2 times 3. And then the minus will be moved to the front and replaced with the plus, and the 0, we won't write the 0 anymore, so this here is the final answer. So just a reminder, when you do a Maclaurin series question, a good idea is to differentiate it first, then put in 0, then put your answers into the Maclaurin series expansion formula. Part B of this question is, using this series, find approximate values for ln of 1 plus 1.05, part B is 1.25, and part C is 1.8. So the first thing we do to find an approximate value of 1.05, an approximate value, not the actual value, an approximate value for ln 1.05. We've already got the 1 in there, so we'll just replace x with 0.05. And we'll put x in as 0.05 on the right hand side, and we get the answer of 0.0487916. If you do that on the calculator, you get a pretty accurate answer here. The next one we're looking to do is 1.25, so we've already got the 1, let's put in 0.25 as x then, and again you replace x with 0.25 and you get a pretty good approximate answer for 1.25. This is accurate to 2 decimal places. And if you put 1.8 in, then your x will be 0.8, because you've already got the 1 in there, and this answer will be accurate to 1 decimal place. Well, it's not even accurate to 1 decimal place. So well, I suppose the moral of this story is that the smaller the x value is, the more accurate your answer is going to be. The Maclaurin series requires more terms to be accurate, as this value of x moves away from 0. So the further away that the input moves away from 0, the more terms you'll need in the Maclaurin series expansion to get an accurate answer. So the closer you are to 0, the more accurate the Maclaurin series expansion is when you stop it at a certain point. The Maclaurin series expansion will go on forever, differentiating, putting in 0, dividing by the number of factorial, but if you're just looking for approximations, then you can stop the Maclaurin series formula at a certain point, and then you'll get an approximate answer. Okay, let's move on to a question then. Find the Maclaurin series expansion for sine x up to including the x to the 5 term. Then use your expansion to find an approximation for sine of 10 degrees. So this is how I would set up my working. I've done this as an extra example to show you how you should set up your working. First of all, write f of x equals sine x and then sub in 0. So f of 0, 0. Then on the next line, do the differential of sine and you get cos, put in 0 and you get 1. Differentiate it again, you get minus sine, put in 0 and you get 0. Differentiate it again, you get minus cos, put 0 in and you get minus 1. And we've got to go up to the fifth term here, so differentiate it once more to get the fourth differential. And put in 0 and you get 0, put it differential again, put in 0 and you'll get 1. So you can see here the nice structure that you can form when you do questions like these. So differentiate it down the left hand column, put in 0 down the right hand column. And now all we need to do is sub these values into the Maclaurin series expansion. We wouldn't do it forever, although the Maclaurin series expansion for sine would carry on forever, but we're only going to do it up to the x to the 5 because that's all it tells us to do in the question. So this is the Maclaurin series up to the power of 5, and now we're just going to put in these coefficients that we've found previously. So yeah, we can see that happening. Put in all the coefficients. F double dash of 0, F triple dash of 0, F4 dash of 0, F5 dash of 0. Lovely jubbly. And we get here the Maclaurin series expansion for sine up to the fifth term. Yes, this would carry on for infinity, but the only term we're asked to go up to is the fifth term. So now we've got to do the next bit, which is find an approximation for sine of 10 degrees. So we can only use the Maclaurin series expansion in radians mode. It's a very good reason. We won't go into it now, but you can only use this Maclaurin series expansion in radians mode. It's because you can only differentiate and integrate and substitute in radians mode. So 10 degrees we first have to convert into radians mode, which is pi by 18. And then we'll substitute x equals pi by 18 into the value of x. And we get an answer there of 0.173648 ... So there we are, that's an approximation for sine of 10 degrees. Alright then, your turn to have a go at these two questions here. Then make sure you've got the Maclaurin series formula available for you to use and have a go at these two questions. Alright then, let's make sure we set our answer up with a good little table format. So the first term is f of x equals e to the 3x. So the first thing I'll do is I'll substitute in 0 and I'll get 1 because anything to the power of 0 is 1. Then I'll differentiate it in the left hand column and I'll get 3e to the 3x. And I'll substitute in 0 into the differential and I'll get the answer 3 because it'll be 3 times anything to the power of 0. We're going up to the x cubed term, so I'm going to have to differentiate it 3 times in total. The next one will be 9e to the 3x. And then when we put in 0 here, we're going to get 9. And the final differential, f triple dash of x equals 27e to the 3x. And f triple dash of 0 is going to be 27. Now we just have to put it into the answer, so it's going to be f of x equals, and if you remember the Maclaurin series formula, it goes f of 0 plus f dash of 0 x, that would be 3x. Then it would be f double dash of 0 over 2 factorial x squared, and then it would be f triple dash of 0, that would be 27 over 3 factorial x cubed, and then that's where we'd stop, but I suppose I should properly simplify my answer. Simplify the final term here, it'd be 1 plus 3x plus 9 over 2 x squared plus, we could cancel out a 3 from the top and the bottom, so that would be 9 over 2 x cubed. And there we are. That would carry on and on and on, but we're only asked to write the series expansion up to x cubed. And for the next one, a little bit more tricky, so f of x here is going to be sine squared. And when we differentiate this, we're going to get f of 0 equals, well, sine of 0 is 0, so 0 squared, that's 0. F dash of x is going to give us 2 cos x sine x, however you wish to do that, product rule, chain rule, however. And f dash of 0, well, that's going to be 1 times 0, so that'll be 0. So the first two terms are 0. Let's move on to the second term. And doing this by the product rule, we're going to get 2 cos squared x minus 2 sine squared x. And then we'll evaluate this at 0, f double dash of 0, that's going to be 2 times 1 minus 2 times 0, so that answer will be 2. So we've got our first non-zero term there. And the final one, triple dash of 0, will be minus 4 sine x cos x for the first term. And then the second term here is going to be minus 4 sine x cos x. And when we evaluate that at 0, so f triple dash of 0, that will equal 0 as well, because wherever we have a sine, we're going to have a 0. So the answer for this question, f of x equals, it's going to be 0 plus 0x plus 2 over 2x, and then it will be then plus 0. So actually the Maclaurin series expansion for x squared is just going to be x. And there we are, that's the answer, so x squared rather, x squared, up to the x cubed term. So there we are, that's the answer for this question. And actually, if I'm right in thinking, the sine squared curve does look curvy. It looks a little bit like that, I'm pretty sure. I think that's right, anyway. Yes, so that's the answer for the questions on page 43, just questions 5a and 5c. On exercise 2c. So make sure you have a go at plenty more of the questions from exercise 2c. This is the main bit of the Maclaurin series section, which will definitely be an exam question in the final exam. So make sure you've had lots of practice at this. Do it in a nice little table format. Differentiation, plug in 0 on the right hand side, write your final answer and simplify down below. It's a really nice little neat format so you can write your answers in here. Lovely, hopefully you found that video helpful, and thanks for watching.